course, my subjective view and why I like being a graph database is that 90% or more of the enterprise use cases are way below the scalability requirements of graph databases and document databases, and way below key value stores. For most enterprise developers out there, the big challenge in the world is just not getting to scale from 1,000 machines to 2,000 machines or whatever. You know, if you have 3 machines or 5 machines or 20 machines, you typically get around, pretty well on that. So that's the crash course in NoSQL. 4 main categories and different focus in scaling to size and scaling to complexity. Now let's dive into graph databases. As I mentioned, there are 3 core abstractions in the graph model. The first abstraction is node. A node is an entity in your world. It has only one mandatory attribute, and that is an ID. Everything else is mapped with properties. But between the nodes, you have relationships. The relationships have a type. In this situation, we have a node that loves another node, and a node that owns another node, and a node that drives another node. This would be pretty meaningless unless you started adding properties to fill it with data. And the properties are key value pairs. And you have, for example, in the node to the left, we have a guy currently called James, who's 32 years old, and his Twitter ID is @spam. You can see here that the nodes a node is the semantic equivalent of a document in a document database. It's a collection of key value pairs. But on top of that, in a graph database, you can also connect the nodes with first-class typed relationships. So I think first-class, as in first-class citizen. And you'll see later on that that actually has implications. For example, you will be able to get a relationship and get an actual object back, a relationship instance, an object, which you can interact with and set properties much the same way as you can with a node. It also, the fact that relationships are first-class citizens is what gives graph databases a real performance edge when it comes to traversing complex data. This is something we will look into a little bit later. One of the most amazing things about graph databases, I think, and maybe from a more philosophical point of view, is what we call whiteboard friendliness. And whiteboard friendliness is the observation that very frequently when you interact with the domain expert, you talk to them about trying to understand their domain, and they're experts in pensions or banking or retail or whatnot, but don't know anything about databases. More often than not, you end up brainstorming on a whiteboard, and very seldomly will they end up drawing tables. As geeks, we've been trained to take whatever scribbles that they and we do on a whiteboard and serialize that into a tabular model. And we have ER diagrams, and we have first normal form and third normal form, and all these different methods and practices for taking sort of the intuitive representation on the whiteboard and getting it into our machines. But an amazing thing that we observed when we first started working with graph databases many years ago, we noticed that these initial snapshots that we took from our brainstorming sessions with our domain experts were reflected one-to-one in the final graph that was put in deployment 6 months later. And I think this is incredibly powerful because I think that the cognitive model of the programmer is actually that of the whiteboard. We, again, may have been taught to, decompose it into tables, but I think the intuitive model for most people when they think about things is like you have an entity and then it's connected to this thing and then it's connected to this thing and it carries some data with it. In this example here, we have a blog. And we call this whiteboard friendliness, and I think that's one of the main reasons why working with graph databases feels so intuitive and is so productive. Okay, I've taken you 20 minutes into the webinar. I haven't showed you code, a single code slide. So it's about time to remedy that. Here is the fundamental API for Neo4j. Here's how you create data into the graph. You have some ceremonial stuff In the beginning, you get the graph database service. In this case, we chose to instantiate an embedded graph database. There are other graph database service implementations. And then we open a transaction. But after that is where the action happens. So from this graph database, we create node, we get a node back. The node is basically a java.util.map. Doesn't really implement that, but that's the semantic equivalent of that. You have set property and get property. The property keys are all strings. The values of the properties are anything that is a primitive type in the JVM, which means bytes and floats and ints, as well as strings. And after we've created our two nodes, Mr. Anderson and Morpheus, we've added some properties to them. We create a friendship relationship by invoking the create relationship to method on the first node. So Mr. Anderson create relationship to Morpheus, and we pass in the relationship type. The relationship types are declared, well, you can declare them in several ways. But in this case, we've chosen to use an enum, social graph type series, the Java language enum, which gives you complete compile time safety. You can only pass in the relationship types that are valid. However, a graph database is completely schema-free in its core, in its kernel, which means that if you create a dynamic relationship type, which you can do as well, the graph database will automatically create the new relationship type when it first sees this new type. There's no need to, create table, alter table, or anything like that. There's no need to do shutdown. It'll just automatically be created for you. All right, there would be no use for putting data in there if you can't get it out there. And there are many ways of getting data out of a graph database, but the core and unique thing is traversals. And a traversal is a way of walking the graph. I'm not going to go into detail about the Traversal API. There's plenty of material about that on the interwebs. But basically, a traversal, as we get back here, is a Java line iterable. As you can see in the bottom few lines of the slide, we get a node back from the traverse, from the nodes method of the traverse method, and that is the recommendation. In this case, we have a traversal, a simple traversal doing social graph recommendations. It uses a so-called open triangle recommendation, which will end up recommending friends to you. We'll end up recommending people in the graph that are friends with your friends, but not friends with you. It's an open triangle recommendation, one of the most popular ones, used very successfully at many large social networking sites. And as you can see, it's a few lines of code using our Traversal API. We also supply a number of graph algorithmic components. In this case, we have a shortest path. And the shortest path crawls graph given two nodes and finds out the shortest way to get from point A to point B. You can imagine this being used on something like LinkedIn. When you visit someone's profile page, you will see how you're connected to that person through the graph. We use the graph algo factory here. We use a factory method on it to get the pathfinder back, and then we get one of the paths and we iterate through it. You can also, this is very successfully used to analyze e-commerce transactions, well, any kind of commercial transactions, to find fraud, to do fraud detection. That's a very common use case for things like that. Okay, so I haven't shown you too much details about the actual core Neo4j API. I want to move on to Spring Data Graph and that API instead, and spend the majority of the time on that. But that's a quick introduction to the Neo4j fundamentals. However, none of this would really matter unless performance was good. No, wouldn't it? And I'm going to give you one example of the kind of performance that you can expect from a graph database like Neo4j. This is an example that was given to us by a large social networking site as a way of evaluating it. The scenario that they gave us was that assume that you have 1,000 people. Every person has on average 50 friends. Now, grab 2 persons and try to see if there's a path between them with max depth 4. So the code in this case is very similar to the previous slide where we found the shortest path between 2 nodes. If you imagine this being modeled in JPA in something like MySQL, then you would have one table that contained IDs and names, like 3 Tobias, 4 Johan, 5 Emil here in this example, and then one table that contains friends relationships. So basically that would contain 3, 7, 7, 4 if 3 knows 7 and 7 knows 4. So 2-column table. Now, to do this one query, you ended up with, I believe it's been a while now, but I believe a 32-way join just to express this in SQL. So just setting aside the runtime cost for this, just writing the SQL code was incredibly heavy. This is what I call, sort of tongue-in-cheek, the sweet spot of suck for SQL, which is arbitrary length queries. We don't know in advance if we're going to be connected on level 1 or level 2 or level 3 or if it's depth 4. And that is really, really difficult to express in SQL. In terms of performance, running this in MySQL on a laptop, actually my previous laptop, with 1,000 persons, we have a 2,000 millisecond query time. So it's a 32-way join on a 25,000 row table, because average 50 friends in the joins table ends up being 25,000 rows. In Neo4j, with the same data, it's a 2 millisecond operation. So that's pretty neat. But we weren't satisfied enough with that, so we decided to up the ante a little bit and add instead 1 million people into Neo4j, and still 50 average friends, so 25 million total connection. Still running on the same laptop, a 300 megabyte heap. And in that situation, we ended up with 2 milliseconds still. So what about MySQL then? Well, we added 1 million people to MySQL as well, and 25 million rows in that one friends table. And we had to abort it after several days. So that's just the kind of query that is incredibly expensive to do in a relational database. Okay, so that's the crash course in graph databases. But what about you if you live in a Spring environment? How can you easily consume and use a graph database? That's where Spring Data Graph comes in, right? So in a nutshell, Spring Data Graph is what we like to say JPA without the suck, or more politically correct, the JPA for graph databases. And we've had a couple of key design decisions guide our development. The first off is, I think, obvious if you're used to a Spring environment, which is that we're going to use annotations to drive the programming model. So normal POJ entities, but you add annotations that then aspects will look at under the hood and take them, use the annotations to figure out how to represent that in the graph. But as Mark alluded to before, we've been very conscious as not to shield the end user, i.e. you guys, from the power of the graph database. We want to make it convenient if you don't want to drop down to the core graph database API on a regular basis. But once you do want to do that, it should be very simple to get access to, for example, the powerful traversals that I showed you before. We've been working on this, as I mentioned, for about a year now, and there's quite a few features. It's been 1.0 now, but we've had commercial projects on it for quite some time. So it's a quite wide feature set. I don't have time to go through much of this. This is an introductory talk, and there will be more later in terms of a more exhaustive walkthrough for the more advanced users. Today I'm going to focus on the top 4 in this feature list.